Hi, my name is Luis Felipe Cadena, and today I will talk about the non-retrievable rotating liner drilling system to overcome challenging, highly stressed rubble zone in a Gulf of Mexico ultra-deep water subsalt application. Worldwide drilling and exploration activities offshore in ultra-deep water have increased in the last few years. Many of the most attractive prospects are subsalt or near salt environments in the Gulf of Mexico, Brazil, and West Africa. The companies are always looking for ways to reduce risks and maximize value in these high-cost environments. Highly technical challenges include drilling through depleted formations, lost circulation zones, weak formations, rubble zones, and tar intervals. These hazards lead to a significant increase in non-productive time, and this means economic losses. This study presents some of the geomechanical drilling hazards in an ultra-deep water well in the Gulf of Mexico, Walker Ridge area. Salt dome drilling took on great relevance because it was discovered that it adds a trap for hydrocarbons. There is an uncertainty for these zones since the characteristics of the subsalt environment in the pressure regimens cannot be determined with precision by means of seismic models. For these reasons, events are commonly inquired, which includes low circulation, stuck pipe, highly stressed rocks, and tar zones below the salt body. Liner drilling method. This drilling system is a non-retrievable system that combines a drilling liner system and a specialized PVC liner bit. A schematic of this system is shown in this figure. The system is designed so that the operator can rim or wash to bottom is necessary, and then continue drilling with the liner to the required target depth. The liner system uses a hydraulic hanger that remains hydraulically balanced throughout the drilling operation and allows for high rates of circulation. The system also uses a running tool that allows the operator to push, pull and rotate the liner and keep it hydraulic balance when in drilling mode. Liner hanger technology. To create a true balance system, hydraulic liner hanger was developed that can be pressured up the push rating of the equipment without the press settings the tool. This liner hanger technology uses dual cylinders that are mirrored, which allow the liner hanger to remain balanced until a ball is dropped into the gear ball seat and the running tool. Hydraulic balance technology. The red arrows are pointing to the upper and lower mirrored cylinders, and by having P1 and P2 equal, This allows the system to remain balanced. PDC drill bit. The drilling bit must meet the requirements of both the inherent risks of the main liner drilling operations and the optimated rope and longevity wheel drilling trouble formation with a conventional PDC bit. A specialized construction with a special internal geometry allows the bit to be drilled out with a special design PDC bit. This PDC bit drills ahead into the next hole section, therefore eliminating the need of a dedicated drill out run. Drill out PDC bit. The drill out PDC bit consists of a standard PDC bit equipped with sacrificial tungsten carbide. These tungsten carbide cutting elements that are designed to engage while drilling out the liner drilling bit. The tungsten carbide elements are designed to wear out during the drill out phase so that the bit's PDC carriers are exposed to drill ahead new formation and reach the next casing point in one single run. In the next figure, we can see a PDC bit with the special drill out designed for liner drilling. Deepwater Gulf of Mexico Walker Ridge case history. When drilling 24 degree, through the thick salt body and approaching the predicted base of the salt, the borehole start to back off. Standby pressure increase and high torque develop, causing the top drive stall up. The PHA was picked off bottom and the well was gaining. The tar was deemed to be very active, and within a few hours, a tar attack followed, including flows, liners, shakers, and the rotary pane. Sidetrack well. The well was sidetracked out of the cement plug at 23,900 feet, and the directional plan was to slightly increase to hold inclination and then drop it back to exit the salt as close to vertical as possible, and to move the well path to 270 feet away from the location where the tar was encountered in the original hole. The next figure shows the original hole and the sidetrack well directional plot. non-retrievable rotating liner drilling system run. The great challenge at the point was to drill through in isolate part of the subsoil highly stressed rubble zone. That was causing most of the wellbore stability problems, and it was also parameters to drill up deep possible and set the liner below the current depth of 25,961 feet to reach the well target total depth without additional string of the liner. At the time the job was complete, it set a record as the deepest and longest liner drilling run successfully accomplished in the Gulf of Mexico deepwater environment. Liner drilling bit drill out run. The figure 6 and 7 show the PDC bit condition after the liner drilling bit drill out and completion of the section in one run. The sacrificial tungsten carbide drill out cores are worn out and the PDC cores are intact. The first is the tar. As documented by drilling cases in the Gulf of Mexico, tar zones usually appears right below the base of the salt. The tar zone location, thickness, and characteristic beneath the salt unpredictable. The base of the salt was never observed in the original well when the tar was occurring. Speculation indicates that it might have migrated through fault line into the salt body, which could explain why the base of the salt was found much deeper in the sidetrack well. Another possibility is the entrampment of the tar just below the base of the salt. The second is highly stressed rubble zone. In the post-drilling analysis, the pore pressure gradient was derived using the logging while drilling resistivity when calibration to the drilling data, such as mud weight, kick, and drilling events. The overburden is mainly controlled by the thick salt layers above. With no salt density, the overburden can be estimated accurately, calibrated on the leak-off test, and the fracture gradient was estimated using the method proposed by Matthews and Kelly, where F is the fracture pressure, P is the pore pressure, and C is the overburden stress.